isomer will have the highest melting and boiling point because it is symmetric. As you can see, one chlorine atom is here, another chlorine atom is in the opposite. So it is symmetric. Any molecule or any compound, if it has to be soluble in water, it has to form hydrogen bonds with water. In the haloalkane, the halogen atom will be substituted by a nucleophile. So such reactions are called as nucleophilic substitution reactions. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry. So today we are back with session 3 of the chapter Haloalkanes and Haloarenes. So in the last session we discussed nomenclature of haloalkanes and haloarenes as well as the nature of carbon-halogen bond. So we got to know that it is polar, right? And as well as the methods of preparation of haloalkanes we have discussed in the last session. So in today's session we are going to study about the physical properties as well as chemical properties of haloalkanes. Right, okay. So chemical properties, in there we are going to study about various chemical reactions which are very important. So in this chapter, the most important things are nomenclature, that is naming of haloalkanes and haloarenes, the methods of preparation of haloalkanes and haloarenes, as well as the chemical reactions of haloalkanes and haloarenes. So these are the three major parts we have to study in this chapter, okay. So coming on to physical properties of haloalkanes. So haloalkanes are colorless, sweet smelling liquids, okay. The lower members like methyl chloride, methyl bromide, ethyl chloride are colorless gases, right. The lower members means which is having 1 to 4 carbon atoms, right, okay. While members having very high molecular masses are solids, okay. So the lower members having lesser number of carbon atoms, those haloalkanes are gases. Then the little middle ones, right, that is 4 to 8 carbon atoms containing, they will be liquids, and the higher ones will be solids, right. And density, bromo, iodo and polychloro derivatives of hydrocarbons are heavier than water. So these are heavier than water. The density increases with increase in number of carbon atoms, halogen atoms and atomic mass of halogen atoms. So as the number of halogen atoms and the number of carbon atoms increases as well as the atomic mass of halogen atom increases, what happens? The density also increases. What is density? Density is mass by volume, right? So when the mass increases, what happens? Density also increases. Clear? So this is the physical properties in general about haloalkanes. Now moving on to the next one, boiling points and melting point. Boiling and melting point. So greater the molecular mass, stronger will be the van der Waals force of attraction, hence higher will be the melting point and boiling point. So this is the first point, greater the molecular mass. As molecular mass increases, boiling point and melting point increases. So how does this molecular mass increase means what? Either the halogen's molecular mass can increase or else the number of carbon atoms increases. Okay, that means from methyl to ethyl, if we consider, ethyl will have 2 carbon atoms, more molecular mass will be there. Hence more boiling point and melting point, right? So now the first point, for the same alkyl or aryl group, boiling point decreases as, that means if the alkyl group is same. So for example, let us take the alkyl group as methyl. So if I have methyl iodide, methyl bromide, I have methyl chloride and I have methyl fluoride. Okay, I have these haloalkanes. So now in that case, which will be the order in which their boiling points will be? The decreasing order will be methyl iodide, methyl bromide, methyl chloride, and in the end you will have methyl fluoride. In the end, you will have methyl fluoride. Okay. So as you can see here, why is that happening? As we discussed, here the alkyl group is same. Carbon atoms, the number of carbon atoms are same. But the molecular mass of halogen is increasing. Iodine is having the highest molecular mass. So, of course, iodine will have the highest boiling point. That is why this is the order. So, it is general representation is given here. Ri greater than Rbr greater than Rcl greater than Rf. I hope it is clear. So, if the alkyl group is same, then what we have to consider? We have to see which halogen it is. Okay. So, this will be the decreasing order of boiling point. Next, for the same halogen, now if the halogen is same, boiling point decreases as the size of the alkyl group decreases. Okay, that means when the size of the alkyl group is increasing, that from methyl to ethyl to butyl if we are moving, what happens? The size increases. Okay, that means number of carbon atoms increases, molecular mass increases, hence the boiling point also increases. So if we consider this is CH3, CH2, CH2X. That means this is propyl halide, right? This is ethyl halide, this is methyl halide. So now in this case, the first case it was alkyl group was same, halogen was different. Now the halogen is same. As you can see, the halogen is same. It can be fluorine, chlorine, bromine or iodine. But the alkyl group changes. So in whichever the alkyl group is the biggest one, that will have the highest molecular mass, hence the highest boiling point or melting point also. Now for isomeric alkyl halide, boiling points decreases as the branching increases. Now this is important. As branching increases, what happens? As branching increases, boiling point and melting point decreases. Now why is that? Let's see. The first one CH3, CH2, CH2X, that is propyl halide. Now this is one form, another isomeric form, another isomeric form, another isomeric form. So this is the order in which their boiling point is present. Now why it is like that? So let us take an example here of butyl bromide, CH3, CH2, CH2, CH2Br. This is butyl bromide. This is another isomer. This is another isomer. So here, as you can see here, in this first, it is the normal structure. Now what happens in the second structure? As you can see, the bromine or the halogen from the first carbon atom, it is shifted to the second carbon atom. You got another isomer. So now it has reached as a branch. Now you got a branch here. Now what happened when you compare this particular and this particular structure, you can see that the size has decreased, right? This was completely in a straight line. Now a branch has come, so the size had decreased. Now again to this carbon atom, we are bringing this methyl group also as a branch. Now what happens again? The size has decreased, right? So that is because as the branch increases, more and more branch increases. From here to here, what happens? Branches have increased. So when branches has increased, what happens to the size? Size will decrease. Now see the size, compare the size of this one and this one. This is lengthy. This is all together, right? So because of branching increases, size decreases. Hence boiling point or melting point also increases. So I hope it is clear regarding boiling point and melting point. As the number of alkyl group increases, boiling point increases. As the branches increases, boiling point or melting point decreases. Clear? So that is very important. Now moving on to the next one. Among dichlorobenzenes, the para isomer being symmetrical packs closely in the crystal lattice and hence has higher melting point than ortho and meta isomers. So we have already studied this. This is in ortho position. If you are considering this particular carbon atom, this is its ortho position, this is the meta position and this is the para position. So this is ortho dichloro, this is meta dichloro and this is para dichloro. So if you are considering these three, which one will have the highest melting and boiling point? It will be in this order, that is para isomer will have the highest melting and boiling point because it is symmetric. As you can see, one chlorine atom is here, another chlorine atom is in the opposite. So it is symmetric, hence it will have the highest melting and boiling point. So I hope it is clear, right? So these points are very important to remember regarding physical properties, right? When alkyl group increases, what happens? When the branching increases, what happens? When comparing para, meta and ortho, which one will have highest boiling point and melting point? Clear? Moving on to the next one, that is solubility. Although haloalkanes are polar in nature, we have already discussed this, the carbon halogen bond is polar in nature, they are practically very slightly soluble in water. In order for a haloalkane to dissolve in water, energy is required to overcome the attractions between the haloalkane molecules and break the hydrogen bonds between water molecules. Okay, so it is only slightly soluble. If it has to be soluble, the hydrogen halogen bond should break, as well as the water molecule hydrogen oxygen bond should break. However, the haloalkanes are not able to form hydrogen bonds with water. They are not able to form hydrogen bonds with water, and therefore less energy is released when new attractions are set up between the haloalkane and the water molecules. As a result, solubility in water is very low. So any molecule or any compound, if it has to be soluble in water, it has to form hydrogen bonds with water. Okay, it has to form hydrogen bonds with water. But in the case of haloalkanes, it does not form hydrogen bonds with water. Hence, the solubility of haloalkanes will be very low. So this is the point you have to remember, because they do not form hydrogen bonds, right? Okay, moving on to the chemical properties. So, we are going to study the reactions of haloalkanes, which is divided into the following categories. The first one we will be studying is nucleophilic substitution reaction. Next is elimination reaction. And the third one is reaction with metals. So, let's begin with the first one, nucleophilic substitution reaction. So, from the name itself, you can say nucleophilic, that means a nucleophile, and substitution reaction means a nucleophile is going to be substituted in place of an halogen, right? Haloalkane, we are studying the reactions about, or the chemical reactions of haloalkanes. So what is going to happen here? In the haloalkane, the halogen atom will be substituted by a nucleophile. So such reactions are called as nucleophilic substitution reactions. Okay, so in this type of reaction, a nucleophile, so nucleophile will be negatively charged species, right, which will be having attractions towards positively charged species, right? Okay, the partial positive charged carbon atom in carbon halogen bond. Okay, so as you can see here, a nucleophile, okay, and this is a carbon halogen bond which is shown here, that is of your haloalkane. Now what happens? The nucleophile will attach to the carbon atom and the halogen atom will be removed. That means instead of halogen, the nucleophile will attach there. The halogen atom will be substituted by a nucleophile. So that is why it is called nucleophilic substitution reaction. A new carbon nucleophile bond is formed here, and the halogen atom leaves as halide ion. It will leave as X minus ion. Clear? Okay. Now the first one we are going to study is under nucleophilic substitution reaction with aqueous KOH or aqueous NaOH. So this aqueous KOH is called as potash or aqueous NaOH. So when an alkyl halide is heated with aqueous KOH or aqueous NaOH, corresponding alcohol is formed. So this is the first nucleophilic substitution reaction, that is alkyl halide. Now the reactant will be alkyl halide, right? Because we are studying the chemical reactions of alkyl halide. So alkyl halide, when it reacts with KOH or NaOH in aqueous state, what will get? The corresponding alcohol and potassium halide or sodium halide will get. For example, methyl chloride, when it reacts with potassium hydroxide, we'll get CH3, and instead of, which is a nucleophile present in KOH, it is OH minus, right? Nucleophile present here is OH minus. So OH minus will attach here, Cl minus will be removed, right? So CH3OH, what it is? Methanol. Now Cl minus is removed, you have a K plus also here which is left. So that will together form KCl. So this is the first reaction. Now the second one is with alcoholic KCN, that is potassium cyanide, KCN. So when an alkyl halide is heated with alcoholic KCN, alkane nitrile, that is cyanoalkane is formed. Alkane nitrile is formed. Okay, so that means the general representation you can see here, alkyl halide when it reacts with alcoholic KCl and when it is heated, what we'll get? RCN and KX, that is cyanoalkane will be obtaining. Okay, for example, we have taken here methyl bromide, it reacts with KCN. What happens? Which is the nucleophile here? It is Cn minus, right? So Cn minus will attach with the carbon atom. So you will get CH3Cn, and what else is left behind? K and Br, which will form KBr, potassium bromide. So this is called as ethane nitrile. So if it is Cn, it is called as nitrile, ethane nitrile, right? The next one is C2H5Cl, which is ethyl chloride, reacts with KCN, and if it is heated, what happens again? Which is a nucleophile here? Cn minus will get attached here, C2H5Cn, which is called as propane nitrile, and KCl will be formed. Okay. Now another possibility is with alcoholic AgCN. We have used KCN here, so what we are getting? Nitrile we are getting. Now another possibility is using AgCN, where we'll be getting isocyanide. Now what is the difference here, KCN and AgCN? Okay, let's see. When an alkyl halide is heated with alcoholic AgCN, alkyl isocyanide or carbylamines is formed. That means this this is your haloalkane. When reacts with AgCN, you can see here RNC is formed, right? And silver halide. RNC is formed, which is isocyanide. Here what it was, it is CN, nitrile. Here it is NC. So that is the difference here. The nucleophile is different here. I hope it is clear. So when you are using KCN and AgCN, you will get different products, which is very, very important, right? So methyl bromide reacts with AgCN. Will you get the same product? Here KCN, you will get CH3CN. But here what you are getting? CH3NC, right? Methyl isocyanide and silver bromide. I hope the difference is clear. Now ethyl chloride reacts with AgCN and heated C2H5NC and AgCl. That is ethyl isocyanide. I hope it is clear. Moving on to the next one, that is with silver salts of carboxylic acid. With silver salts of carboxylic acid. When alkyl halide is heated with silver salt of carboxylic acid and ester is formed. So what is the silver salt of carboxylic acid? What is carboxylic acid general representation? RCOOH. Right. So silver salt means instead of this hydrogen, there will be a silver there. That is RCOOAG. Silver salt, right? So this is silver salt of carboxylic acid. So the silver salt of carboxylic acid reacts with RX. What is RX? Alkyl halide. What do you get? RCOOR. Now what is this general representation? This is ester, right? R C double bond O-R. This is what? This is ester, right? So you get an ester as well as a silver halide. Now let's take a particular example, CH3COOAG. So this is silver acetate, as you can see. Again, it's a silver salt of carboxylic acid. Which acid it is? Methanoic acid, right? Okay. And we have taken methyl iodide here. So what is going to happen here? The methyl will get attached to this carbon atom and the silver iodide will be formed. So you will get methyl acetate, which is ester, and silver iodide is formed. Another example, C2H5COOAG. Silver salt of carboxylic acid reacts with C2H5Br. Now what happens? This will get attached to this carbon atom. You will get ethyl ethanoate, that is C2H5COO, C2H5 and AgBr. So I hope these reactions are clear for you, wherein we were studying about the different nucleophilic substitution reactions. So the first one was with KOH, which is the nucleophile OH. OH minus will be substituted in place of halogen. Next is KCN, CN minus will be substituted. In case of AgCN, NC, you will get an isocyanide. And carboxylic acid, that is silver salts of carboxylic acid, you will get an ester. Okay. So I hope it is clear. Now let's take the different reagents, and from these reagents, which are the nucleophiles, what will be the substituted product that you are going to get, and which is the class of the main product we are going to see. So if it is NaOH or KOH, just now we have discussed which will be the nucleophile here, that is which is a negative part here, it is OH minus, right? So this OH minus attached to the alkyl group, and which is the product formed, it will be an alcohol, ROH, right? R and the nucleophile, which is the nucleophile OH. So OH minus and R together forms ROH, which is an alcohol, right? Now H2O, in H2O also, which is the nucleophile, it is OH minus. Again, you will get an alcohol. The next one is NaOR dash. Okay, so here which is the negative part, Na plus, and OR minus is the negative part, that is your nucleophile. Now this will get attached to the alkyl group, right? So already alkyl group is here, this will get attached, so you will get ROR dash. What is this general formula for? It is for ether, right? It is not ester, it is ether, right? Next one, sodium iodide, which is the nucleophile, it is I minus. So you will get alkyl iodide, which is alkyl iodide. Right. Now the next one is KCN. We have already discussed. It is Cn minus. You will get RCN, which is called as nitrite or cyanide. Right. The next one is AgCN. It is reverse. You have to be very careful. It is Nc minus. You will get RNC, which is called as isocyanide or isonitrite. So that is cyanide and isocyanide. Okay. If you are using KCN, you get cyanide. If you are using AgCN, you get isocyanide. Next one is KNO2. Of course, here NO2 minus it will be. Okay. So ONO minus it is. So it will attach to the alkyl group through the oxygen atom. Then you will get an alkyl nitrite. Okay, the next one is AgNO2. If you are using silver nitrate, here the nucleophile is NO2 minus. So again, you have to see the difference here. If you are using KNO2, the NO2 minus, that is your nucleophile, will attach to the alkyl group through oxygen here. You can see here, it is through oxygen. But if you are using silver nitrate, it will attach to the alkyl group through nitrogen. So this is the difference. So this is called as nitroalkane. right? So alkyl nitrile and nitroalkane. So this is the difference. If you're using KNO2, what is a product? If you're using AgNO2, what is a product? That is, the alkyl group can bind with NO2 through nitrogen or oxygen. Okay, based on that you have alkyl nitrile or nitroalkane. Next one is RCOOAg. This also we have discussed what it is. Silver salt of carboxylic acid. RCOO minus is the nucleophile here. So you get R-COR, which is ester. We have just discussed this now. The next one is lithium aluminium hydride, LaLH4. H minus is the nucleophile here. It binds with the alkyl group and forms or substitutes in place of the halogen and forms RH. You'll get a hydrocarbon, right? The last one is R-M plus. The R minus will be the nucleophile. R will be formed, which is an alkane. So I hope this reagent nucleophile and what is the product formed and which class it is, I hope it is clear. So these two are very important. That is, when we use KCN and AgCN or KNO2 and AgNO2, what will be the nucleophile? So I hope that is clear for you. So in the next session, we are going to study about substitution nucleophilic unimolecular, that is SN1 and SN2 mechanism in detail we are going to study, which is very important. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.